Hi, this is a video about continuous probability distributions. So it's about random variables with a continuous distribution, and they behave a bit differently from discrete probability distributions, like, for example, the binomial distribution. And one of the things that really stands out is the following thing. If I take something like an exponentially distributed random variable, and I ask what is the probability for one certain outcome, so what is the probability that x equals a specific value x? And the answer is 0. So for a continuous distribution, the outcome for each individual value is 0. So the function that is used for computations here is definitely not 0. So this function here is not a function that gives the probability. Instead, it's what is called a probability density function. Probability density function, and it's usually denoted with by a rho. And using these functions, you can compute probabilities, but they will not be probabilities for a certain specific outcome, but more likely for a range of possible outcomes. So, well, let's zoom into this example. I'm going to actually do two examples, the exponential distribution and normal distribution. First, this one. This is a nice example for waiting times for a bus. Say it's in quarters of an hour, and then this could be the distribution function for a random variable telling you what the probability is that you have to wait a certain time in quarters of an hour. And yes, if the bus goes on average every 15 minutes, every quarter of an hour. So suppose then that I would like to know what's the chance that I have to wait a certain time between 15 and 30 minutes, or that is between 1 and 2 quarters of an hour. So that would be the probability that x is in between 1 and 2. And now comes in this probability distribution function, because the probabilities are computed by computing the area under the graph of this distribution density function. So if this is 1 and this is 2, the probability of waiting between 1 and 2 quarter hours is the area under the graph like this. And I hope you know, otherwise I tell you now, it's computed by the integral over the probability distribution density function. So it's the integral from 1 to 2 of rho of x in x dx. And of course we can compute this more precisely by filling in the equation. It's a function, it's this, and we can find the antiderivative, which is minus e to the power minus x, and then we just plug in the boundary values, and there you go. You get minus 1 over e squared minus 1 over e, or so it is 1 over e minus 1 over e squared. All right, so in continuous case, you have to integrate to find probabilities, and the boundaries depend on what specific interval you're interested in. And yeah, the probabilities for a single value are 0, which also, that's what you get if you would integrate from 1 to 1, the outcome is 0. So it also doesn't matter whether you put strict inequalities or equalities like this. A single value doesn't add to the integral. You can also use this probability density function to, for example, compute the expectation value. I'm not going to do it right now, but for example, the expectation here of the value x would be the integral of x times the probability density function dx. And also the variance and standard deviation are defined like this in terms of this probability density function. So this is really the defining thing for a continuous probability distribution. Now look at this other example here. It's a very famous distribution. It's by far the most important continuous distribution. It's the normal or Gaussian distribution. Now why is it so famous? Why is it so important? Because it occurs all the time in many experiments, real-life experiments. Your variables will have this distribution, and it has something to do with it. If you take the sum of many random variables and you look at the outcome, then there's a famous theorem that states that this distribution of the sum is always approximated by a normal distribution, well, under some conditions, but very generally. And of course, when you look at complex systems, then the variables will actually also be composed in that sense of many underlying random variables. So that's why this normal distribution comes up a lot. So let me describe it a little bit qualitatively. There are two parameters. So we're now looking at this y, which is normally distributed. And there are two parameters which sort of set the shape of your graph, of your distribution function, and generally which determine the distribution function. And you can see here a mu and a rho. Mu and rho. And the mu, and actually there's a very nice and simple interpretation of this. I'm not going to make the computation, but if you would find out that actually mu is the expectation of y, and rho is the standard deviation of y. So pretty important parameters, and they determine the shape of this, again, a very famous graph. The normal distribution or Gaussian distribution always has this clock shape. And what can change is the position of the clock. You can translate it horizontally depending on the expectation, which is mu, which is x is mu is exactly the symmetry axis of the clock. And rho, the other parameter, determines the width, as it's the it's the standard deviation. So if rho is small, you would expect a narrow distribution of the values, and if it's big, a wider one, and it translates into the width of the clock. And well, of course, there is a formula for rho, and it's written here. It's 1 over, and then here's sigma square root of 2 pi. This is a factor to make sure that the integral over the whole distribution function is 1. Because if I integrate the distribution function, the density function over the whole domain, then of course we have the chance that anything happens which is always 1. So therefore you have here this normalization factor, and then here is an exponential function within the exponent minus 1/2 times x minus mu divided by sigma, and then the whole thing squared. You also recognize this minus mu, which is, x is replaced by x minus mu, which is simply this translation, this horizontal translation. Okay, so this formula is pretty important, but it has one rather bad quality. That is, if we want to compute the probability of y being between two finite values, a and b, well, we now know what to do. We have to integrate our density function over the interval there. And then comes the big issue that for this specific function, this integral is not computable because it does not have an antiderivative expressed in functions that we know. Actually, the antiderivative of this function is taken to be a new function. And it's sometimes called the error function. for other reasons, I'm not going to discuss now. Sometimes it's just called, like on your calculator, it might be called normal CDF. Normal CDF on the graphical calculators. So there's actually no way for finite values here to compute this, these outcomes exactly. So it will always be an approximation. So this is one of the mysteries of nature, or special things, that exactly the distribution that you need the most has this specific quality. Anyway, now you've seen the most important continuous probability distribution, and you've seen some of the special properties of this, and I hope it will help you further.